Hello and welcome to another video. Today we're going to be doing minimum operations to reduce x to 0. And honestly, this problem is, once you figure out the trick, it's a really easy problem, but the trick is kind of difficult. So let's go through it. You're given an integer array nums and an integer x. In one operation, you can either remove the leftmost or the rightmost element from the array and subtract its value from x. Note this modifies the array for future operations. Return the minimum number of operations to reduce x exactly 0 if possible, otherwise return -1. So in this first example, we have 1, 1, 4, 2, 3, and we want to get 5. So what we would do is we would just take the number from the right and the number from the right again. And let's just draw this bigger, just to kind of show exactly what I mean. So essentially, at every time you have a choice, either take the right number or the left number, and you want to try to minimize the amount of operations and take the numbers to get exactly 5. And so the best solution would be to take 3, then 3 gets removed, and now we can either take 1 or 2, and you can only take from the end, so then you would take 2, and 2 would get removed, and you would get 5 total. Then in the second example, I'm not going to draw this one out because it's pretty straightforward, so we have 5, 6, 7, 8, 9, and we need to get 4, so that one's not possible. Let's draw the third one. 3, 2, 20, 1, 1, 3. And we want to get 10. And so here to do that, the optimal solution is, you can see like we don't want 20 obviously, but we're going to want to take this 3, we're going to want to take this 3, which would be 6, and then the order doesn't really matter here. We're going to want to take 2, 1, and 1. So we're going to need to take 5 numbers and just leave the 20. And so our answer would be 5 there. And basically, we need to figure out how to do this efficiently, but the problem comes that we have a very big array, right? We have 10 to the 5th. So I think the thing that people would come up with like first, and it's pretty intuitive, is some kind of DP. And let's think about like how many states we would need to represent the DP, right? So we would need a lot, because we need to figure out like what's the left bound, what's the right bound, and then we'd also need to figure out like what our target is, which gets really expensive, right? So you can just say like, well, I'll just make a DP with some kind of caching, and I have 2 options, right? I can either take the left number or the right number, and let's just maybe go through those and figure it out. But the problem is, left is 10 to the 5th, right is 10 to the 5th, and target is like 10 to the 9th. So this is like an n-cubed solution for DP. And so you can't really do DP for this. That's why it's a little bit counterintuitive. Like if there was a way to do DP for this, let's say this was a smaller array or something, or there's like nothing else you could do, then it would work. And there is another way of doing it with like prefix sums that I think it's like an n log n solution. I'm not going to talk about it here, partly because A, it's harder to come up with, and B, it's less efficient. But there is a way to do something with prefix sums, and you can think about it that. You can think about that if you want to. Essentially, it would be something like you would make prefix sums for the left side and the right side, and then for every single number, you would just try to find like what's the, because your left and right sums are ordered, right? Like if you just start summing from the left and the right, it would be something like 3, 5, 25, and so on for this side, and then similarly from the other side, it would be like 3, 4, 5. And so you would do something like for every single number, just try to find the matching number in the other sum that you need, and then get the index, right? And so what would happen there is, like, let's say you go through this part, it would be n, and then this part would be logarithmic because you can binary search through this side. But I'm not going to talk about that in too much detail, so that's like an n log n solution if you want to do that. Like that kind of solution would be a medium hard to hard solution. But the one that we're going to talk about is actually really straightforward. So instead of focusing on like where to remove things, we basically need to reword this problem into something that's a lot simpler. So let's say we have an array of a bunch of numbers, right? Like 0, 1, 2, 3. It doesn't have to be sorted. But essentially, if we have this and we have some target, instead of trying to figure out like what side to remove from, all we actually have to do is, like, let's say we have a sum, right, called sum. Let's just say we have an array sum. Like this array sums up to this sum. And we have some target that we want to get, that's this x value, right? Well, instead of trying to get this target, instead, what we can do is we can try to find the longest array that sums up to sum minus x. Because if we have an array that sums up to sum minus x, right, that array, sum minus x plus x equals the total sum. So if we have an array that sums up to this, then the rest of the numbers are going to have to sum up to x, right? And so what we're going to actually do is we're going to try to find the longest contiguous array that sums up to the sum of the array minus the target we're looking for. And let's say it's like something like this. Well, now that we know how long this is, no matter what this is, think about like how many numbers are left, right? Like this is the array that we aren't going to use in our calculation, right? This is sum minus x. We can easily figure out how many numbers we need to get that x, right? It's the length of the array. So let's say this is like 1, 2, 3, 4, 5, 6, 7. This is 9 numbers total, and the length of the array is 6. That means we would need 3 operations because we would need the other 3 numbers. So just to make this a little bit easier, let's go over this example. Let's go over this, or maybe we can actually go over both of them, just to make it like a lot easier to understand. So let's say we have 1, 1, 4, 2, 3. So what we're going to do is we're going to first sum up the array, right? So this array sums up to 11. So sum equals 11. Actually, draw the 3 better. There we go. And our target is 5. So x equals 5. So sum minus x equals 6. And so we want the longest consecutive array that sums up to 6. And then we're guaranteed for the numbers that we don't use in the array, that will sum up to 5. And so let's kind of like look at this. So what's the longest array we can see that sums up to 6? That has to be continuous, right? Well, it's probably going to be something like this, right? Because this also sums up to 6, but this is shorter. So let's maybe use another color. And that part is pretty straightforward. I'm not going to go through like exactly how to do that. That's just a standard sliding window, right? You just sliding window, and then you just check the sum, and every time your sum is too big, you just make it smaller. That's like a super easy sliding window problem that I'm just going to code up. So essentially, that's what our problem comes down to, is we need the longest array, the longest consecutive array that sums up to 6. And like I said, standard sliding window, you just check if your current array is less than x, you don't do anything. And then if your current array is greater than x, you have to keep removing things to make it smaller than x. Finally, you check, is the length of your array x? So I guess we can kind of draw that in a picture real quick. So like what would happen is I'm going to draw a line that represents our sliding window. So we would take like this number, our current sum would be 1, we would keep going. Take this number, our current sum would be 2. Take this number, our current sum would be 6. So now we actually do have a match for something that has a sum 6. So we would record that length. So that length is 3. And then we would keep going. So our current sum would be 8. So we're going to have to delete some stuff, right, to make it 6 again. And so it would look like this now. And now this would be length 2. And we want to just keep the longest one we had. So then we also add this. And then this once again gets too big. This becomes 9, right? So we can get rid of this. And now our sliding window looks like this. But now this is smaller than 6, so that's not a valid answer. So as we did our sliding window, our best answer was this, length 3. And so because that's length 3, we can simply say, okay, well, the length of our array is 5. Something with length 3 is 6. So then the rest of the numbers have to add up to 5, and they do, right? So these numbers add up to 5, and how many numbers are there? Well, it's just the length of the array minus the biggest length we found. So just 5 minus 3, which is 2. And that's our answer. And let's do the same thing for the second example, and then we'll code it up. So yeah, like once you understand that little trick, that instead of focusing on how to remove things, just find the longest possible array that sums up to sum minus x, it becomes a pretty easy problem, like a medium to easy-ish problem. Okay, so now let's do the second one. So 3, 2, but I did say that trick is not super easy to find. So this problem is maybe not like the greatest, because it's literally just like, can you find a trick? If you can, you solved it. If you can't, too bad. Okay, so let's do this one. So we're trying to get 10. And what's the total sum of our array here? So we have 25, 30. So we are trying to get an array of sum minus x, which is 20. So we're going to do the same thing, sliding window, the longest possible sum sliding window that sums up to 20. Okay, well, let's see what happens. So this is too small, too big. So now we're going to have to delete some stuff. And so our sliding window will just be one element here. And because it's one element, it's going to be length 1. Then we keep adding. That is too big. So then we have 1. Then we keep adding. And these are all too small. So our answer here would be 1, right? For the maximum sliding window, we found that the sum is 20. And there are 6 elements. So if the sliding window is 1 element, the rest of the elements we need, and those are guaranteed to sum up to 10. So 6 minus 1 equals 5, right? The maximum sliding window is this one right here. So if we need this, then everything else is part of the x, which is 5 operations, right? And we're guaranteed, like no matter how you draw the sliding window, you literally just look at how many numbers there are left, and then the order that you get them doesn't matter. They're guaranteed to add up to x. So it would just be the number of numbers that you have after that sliding window part. And that is the answer. So just to remind us one last time what we have to do, essentially we have to get the sum, we have to get the sum minus x, and then we have to get the maximum sliding window that equals sum minus x. And there are going to be cases where that never happens, right? So if that never happens, then we have to return -1 because then we can't get x, right? So like let's say our sliding window that we needed is like 50 or whatever, that would be the no solution. And so we can actually look, right? So we can actually look at this problem really quick. So what's the sum here? So it's 17 plus 7. Let's actually do this one as well, actually, just to do this, just to show like a no solution type of thing. So 5, 6, 7, 8, 9, and we are looking for 4. So our sum here is 11, 18, 26, 35. So sum 35, x is 4, sum minus x is 31. And obviously we can't get that, right? So we're never going to get a sliding window with a sum 31 because this is 35. So it would have to be like all the numbers but 1, and that number has to be 4. So we're never going to get that. So if we never get a sliding window that has sum 31, then we're guaranteed that x is never in here. Also, we are going to do a check in the beginning, it also makes it faster. Let's say our x is actually something like, let's say our x is like 0, right? So if our x is 0, then we're also going to probably want to, we can just like return early or something. And I think our x can be 0. Also, our x can be the entire sum, right? So if our x is the entire, like let's say our x is 35, then our max sliding window is actually going to be going to be 0. So if sum minus x is 0 or x is 0, we can return right away, right? Like if x is 0, that means we don't need any numbers, and if if x equals the sum, then it's the whole array. So we can just return early for those. So those are like, base cases we can check for. Okay. And so now let's actually code it up. So we are going to get this like array sum that's the sum minus x. So we're going to get an array sum that's the sum minus x. And if this is 0, that means x is the entire array, right? Like that means x equals the sum. So we can just return here. So if array sum equals 0, we can just return length nums because we have to use every single number. And for some reason we are getting a thing here. There we go. Okay. So now we make a standard sliding window, right? So result equals 0, left equals 0, cur total equals 0, that we're going to use to keep track of the total. And then what I'd like to do in the sliding window is I use the right as we traverse through the list. So I'll just say for right in range length nums. We are going to add to the current total. And we're simply going to say, if it's too big, let's just keep making our array shorter. So while cur total is less than array sum, our goal is to get the array sum, and left is right. Because you don't want the left to go like out of bounds or anything, right? Like let's say the current number is like 30 and the sum we want is like 20. We don't really need to, we need to have some kind of constraint to make sure that left doesn't go out of bounds. Okay. So we could say cur total minus equals nums left. We're essentially just, this is our shrinking section. So we're going to shrink it until either left equals right or the array actually is, is the current total is less than the number we're looking for. And we still have to check if they're actually equal, because it might be less than the number we're looking for, or it's still actually possible for it to be bigger if it's one element. So if we can just check if current total equals array sum, that means we have a valid sliding window. So then we just try to maximize our sliding window. So we can say res equals max res, right, minus left plus 1 to get the length of the current sliding window. That's pretty standard sliding window. And now that we're done with this, we need to actually check, right? So we need to actually check if we got a sliding window, because we might not have a valid sliding window. So we just need to have a check here. So we can just say return length nums minus result if result doesn't equal 0. Otherwise, let's return -1 because we didn't find a valid sliding window, right? If result is 0, we never found a sliding window, so we're supposed to return -1. So let's give that a try, and let's actually bring this up here so you can see it does work. And you can see it's pretty efficient as well. And yeah, but literally this problem is just, can you find this trick? I do think if you do the like 2 arrays, like I said, with a prefix sum on both sides and a binary search, that's like a medium to hardish solution, but this one is definitely like an easy to medium solution, just as standard of a sliding window problem as you can get. And so let's go through the time and space for this one. So time and space, time, standard sliding window, right, O of n. Space is, we made an array sum, which is a variable, which is just like a normal variable, result, left, card total. These are all not dynamic, right? They're just small variables, not dynamic, that allocated memory. So this is going to be O of n space. And yeah, hopefully you like this one. I'm curious about like what the reviews are. It is pretty positive. So yeah. But yeah, I think I want to say I'm not a huge fan of this one because the actual algorithm part here is not very hard. It's mostly just, can you figure out the trick? But in either case, if you did like the problem, please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.